All right, let's take a look at a little longer, more extensive example. It's not too much more complex. The idea here is that we're going to take a large array of integers and figure out the smallest value in the array. In order to parallelize that, I'm going to take the original larger array and I'm going to chop it up into smaller segments, one segment per thread. And then each of the threads is simultaneously going to search its segment to find the local minimum within that segment. And then it's also going to determine if it's found a smaller minimum than any previous thread has found, and if so, update a global minimum. So at the end of the process, we'll know the smallest value in the entire original array, except hopefully we'll go faster to accomplish that. And just to give you a sense for what comes out of this function here, this program as it's running, the program's called Listmin. I'll put up a listing on the website. You can see here, first of all, that I've got this output that says P00 through P03. That's actually output coming from each of the threads, and in this case it's showing up sort of as the thread finishes up doing its thing. So it's going to tell me that it's sorted through 16K integers, the address of the beginning of that array of integers, and then the local minimum that it found. Notice that these are coming out of order, right? Because these are going to show up just whenever each of those threads completes its execution, it's going to print this message before it kind of returns back to join with the main thread. So we see thread 0, then thread 2, then thread 3, then thread 1. And if we were to run this again, we'd probably see things taking place in a different order. The text here that says thread 0 returned and then that value, this is coming from the main thread. And I'm just kind of showing here how the main thread is receiving the values back from the underlying threads. And so we can see sort of when the main thread joins up to those threads as they complete. And then the main thread also prints out the global minimum value, and it's also keeping track of some runtime information, which we'll take a look at in a second. So nothing particularly earth-shattering here, just a simple parallelization of a minimum finding algorithm. So let's take a look at the code. Here's the source file for listmin.c. There's some header files we're bringing in. You can see the header file for the Pthreads themselves. And then here's our global minimum. Because I've written it in such a way that each of the threads can write to that global minimum as they're finishing up their segment of the original array. I've got to put this in memory someplace where all the threads can access it. And as we talked about previously with the pointers and the earlier threads talk, we need to put that in basically static data that's going to be available to all of the threads. We can't allocate it locally within a thread for sure. We could also have put this in dynamically allocated memory on the heap, but this is a fairly easy way to store just a simple integer. I'm also initializing this to int max. That comes from this limits header file, and it's basically an architecture-specific constant that says here's the largest integer that we can store on this machine. That gives us a sort of a starting point for comparing with the values in the array itself. And of course, because I'm going to have multiple threads that are going to be updating this global minimum, in order to avoid them stepping on each other's toes, I'm going to also use a mutual exclusion lock. So I've declared a mutex here called global min lock. You can see kind of the naming convention connects those two up in order to allow the threads to have exclusive access to that global min variable inside of a critical section. Now, unlike the previous example, here we're going to do a little bit more in the way of passing information into the thread's start function. In particular, we want to be able to partition the original array into smaller chunks. So let me scoot down here to the end and show you the main thread. So here's the list that we're sorting. So big list, and it's defined to be of list size. Let me just walk up and show you what list size is. So here's some sharp defines that are convenient to be able to sort of put in magic numbers without having them leak all over the code. So again, I'm going to just run 4 threads. I could change this to be whatever value that I want. Each of the sublists, or what I've been calling the segments of the original list, those sublists are going to be 16 times 1024, or 16K. So 16K integers, which is going to actually be a fourth the size of the amount of memory because it's 4 bytes per integer. And then the overall list size is going to be the sublist size times the number of threads. So if I wanted to try this on 8 threads, I could get sort of similar comparative performance numbers by just bumping up the num threads, and now I'd be sorting more numbers on more threads. So this is just a kind of a handy way of coming up with these values. So down here, when I declare big list to be of list size, I'm saying I want this to be 4 times 16 times 1024 integers, right? So 64,000 integers that we're going to search through in big list to find the smallest values. The values that I'm going to put in the big list to test this program, I'm just going to put in random values. So the sRandom is the way that we seed a random number generator that's part of the standard C library. And a really common way to do this to get different values each time you run is to just go ahead and grab the time, which is just the real-time clock on the Unix system, and then pass that time as the value for this sRandom. So sRandom stands for seed random. We're seeding the random number with a new value, and that value is going to be basically dependent on when we run the program because we're reading the time from the clock, which means it's going to be different each time. Sometimes you don't want to do that. If you want to test what's considered to be a random number, but you want it to be the same random number every time, you can actually do sRandom with a fixed value, with a constant, and then actually the sequence of random numbers that you'll get from this pseudo-random number generator is going to be the same each time. In our case, we want them to be different each time, so I'm grabbing the time. So from that random number generator, I'm going to initialize each of the elements of big list with a value that's defined here to be random, and that's the actual random number that's going to come back. And I'm going to just divide that by 5 to keep the numbers in a reasonable range. And then obviously this is just going to iterate over from 0 to list size -1. So that initializes the list. Now what I want to do is I want to partition that list into different sublists to hand one of those sublists to each of the threads. So when we run the threads, so here's our pthread create. You'll notice that we've got a for loop here that's iterating over the number of threads. So this is going to go from 0 to 3 in what we've got so far. And then I'm setting up this structure called Threadargs, and I'll go show you the declaration of that in a second. But when I'm done setting that up, when I call pthread create, I'm passing one of those Threadargs structures to the start routine for the thread. And that's what's going to kind of tell the thread itself, here's the portion of that array that I want you to focus on to do this calculation in parallel. In the previous example, I think we just passed a null value here because I wasn't giving anything of interest to the start routine. We still have to have a parameter because C doesn't have variable argument lists, or this doesn't have variable argument lists in this case. In this case, we want to actually kind of configure each thread differently, right? I've got this one big list, and it's stored in memory, and I want to have each thread access a different chunk of it. So the first quarter of the values in big list are going to be solved by thread 0, the next quarter by thread 1, and so forth. So let's go look at the declaration of that structure. Here it is. So we've got a structure. It's got four elements in it. The first of which is the thread ID. So back here when I showed you this output from the different threads, it says P00, P02, B03. That thread ID is the number that's represented there. Because we're not guaranteed the structure of the underlying kind of pthread T thing, right? That structure that keeps track of information about each thread that's created. We don't have any guarantees about what's inside there. My suspicion is it actually is probably a small integer, although I didn't go check for that, on this particular implementation of threads. We can't guarantee that, and I find it really helpful, particularly when I'm generating debugging output like this, right, to be able to have a repeatable identifier that lets me tell one thread from another or one processor from another in a distributed memory case. So I just choose to add this thread ID to the structure so that when I print output like that, I can just grab my thread ID, right, whatever thread I am, and print that out in a repeatable way. So that's just for bookkeeping. The second thing here is a pointer to an integer, right? We're sorting an array of integers, and we know that an array is the same thing as a pointer to the first element. So what we're doing is, in order to tell each thread which sub-array, which sub-list to sort, is we're passing it a pointer to the first element that it's supposed to pay attention to. So that's going to be a different value for each of the different threads as they get started up. Then we're also going to pass the size of the list, and in this case, again, it's the size of the sub-list that each thread is supposed to sort. Because of the way that we've set up this list, those are all going to be the same value, right? They're going to all say, hey, you're supposed to sort 16K integers, because that's the way we define things down here to say that the sublist size was that big. But if we had some arbitrary sized list that wasn't a power of 2, or that wasn't an even multiple of anything interesting, or a multiple of the number of threads, that value might be different for some of the threads. And then we're also going to pass in a place to store the local minimum, and we'll see how that works here in a second. So this is our structure. This is not a Pthreads specific thing. This is something that's specific to our application, where we're setting up this structure so that we can pass this to each of the threads in the start routine and allow that thread to kind of configure itself properly to access the appropriate elements of the list. So let's go back down here and take a look at how this is being set up. So for each of the threads, I'm just iterating over this control variable I, and I'm setting up the Threadargs structure for this particular thread. Where's that defined? Well, up here, you remember that here at the top, Threadargs T is what I called that, right? I didn't start it with Pthread because I don't want to confuse things with the Pthread library itself, but that's just our structure to carry this information that configures each thread. So Threadargs T, I'm declaring an array of these things because I'm going to have to construct one for each of the threads and pass it to the thread as I'm starting it up. So I've got num threads of those structures, and here inside of the for loop that I'm using to kick things off, I'm going to initialize one of those at a time and then hand it off to the start function for the thread. So Threadargs of I, so this will be the Threadargs of 0 for the first thread, Threadargs of 1 for the second thread, and so forth. So Threadargs of I, I'm setting the thread ID to 1 or to I, right? That's how I get those 4 unique values for the thread IDs in my debugging output. Again, because although thread IDs is an array, right, and we know that which is a pointer, and we know that if we have a pointer to a structure, we use the arrow function. But in this case, we're taking that array and we're coming out with a specific element of the array, right? The ith element, 0, 1, 2, or 3, which means that we have an actual structure, not a pointer to a structure, when we get to the dot here. So dot thread ID equals I. We also need to tell the thread where in that big list to start doing the search for the smallest value. So just as a kind of a simple way of doing that here, I've defined an integer pointer called next sublist, and I've initialized it to big list, right? So big list is actually going to be allocated here in the main function. What I want to do is basically grab sections of big list to hand them off to the individual threads. So I'm going to use this next sublist pointer as the location for the next thread that I start up to begin doing that search. And for the first thread, I just want to start at the beginning of the list, so I initialize this to big list. Okay, so this second value here in the Threadargs structure is the pointer to the first element I want to search. And I'm just going to set that to be next sublist, and we'll see that we'll update the next sublist here in a second. So the first time through this loop, I'm going to point to the beginning of big list. Then I'm also going to pass into the thread the number of integer values I want to have it search starting at this location. That's what the list size does. And I'm just going to use the constant that I defined before, right? I'm just cooking that up for this example. And again, if this was an arbitrarily large data set, I might want to set this to be, the size of the array divided by the number of processors plus or minus 1 or something like that. But in this case, we know that all the sublists are the same size, but I just decided to pass this in as another one of the parameters to the thread. Now, as I'm getting ready to start up the next thread, I want to be sure to update that next sublist pointer so that it points to the next segment, the beginning of the next segment of the big list array. So I'm going to take next sublist and add to it sublist size. So this is an example of some pointer arithmetic. When we do an addition operation like this on a pointer, we don't just add that integer value necessarily. We add that integer value times the size of each of the things being pointed to. So in the case of our big list, each of the elements in that list is an integer, right? So it's 4 bytes. The size of that int is 4. So when we do pointer arithmetic, if we add 1 to the pointer, what we really want to do is advance not to the next byte in memory, but to the beginning of the next integer in the array. And in this case, I want to skip over all of the integers that are being allocated to this particular thread so that the next time through this loop, I'm pointing to the integer following that original subset. So by adding sublist size, I move this next sublist pointer, remember defined right here, I move that to the beginning of the next sublist. So in this particular case, it's going to advance, by 16,000 integers. Okay. Finally, I'm also going to be harvesting the local minimum value from each of the threads. And just to give this guy an initial value, instead of having just garbage in memory, I'm initializing it to something that's invalid. I mean, I'm not going to have minima that are less than 0 because of the way I generated the random values. But I want to give this thing some value, which is often really helpful when you're doing debugging on these things, right? Because if you go look in memory to see what the value of these elements of this structure are, and you see some value like -1, you say, well, somehow we didn't actually write the proper value there because it's still the initial value. So good to give everything some initial value before you kick things off. Okay, and then finally, we can create a thread. So we're using that same idea that we've been talking about, where this Pthread T structure type is the opaque data structure that's used by the Threads library to keep track of the details of each individual thread. And because I have num threads, 4 threads in this case, I'm going to create an array of those things. So when I create a new thread, I've got to give the address of one of those Pthread T things to the thread library so that it can start up the thread and then fill in whatever information it needs into that location in memory, so that later on my main thread here in my code can refer to that to do things like join the thread as we're ready to complete the execution. So I'm going to again take threads of I, which gives me the structure, the Pthread T structure, but Pthread create needs to be able to write into that. So I can't just send the structure, which would copy it. I want to send the address of the structure, which is going to allow Pthread create to update that for me so that I can refer to it later to control the behavior of those individual threads. This next parameter is for kind of setting custom attributes on the thread. We're just going to take the defaults. The third argument is the start routine, right? This is the code just up above here that we're going to focus on next that actually finds the minimum value in the portion of the big list array that's specified by the details that we just set up right here. And we pass that information here in the fourth argument to Pthread create. So Threadargs, that's what I just got done setting up with the thread ID, the list pointer, the list size, and the local min. I'm passing in Threadargs of I because I'm currently starting up the ith thread, and I need to pass that as an address, so the ampersand needs to be there as well. Okay, and just like before, I'm using this little check thread return thing to verify that the return value that I get back from the Pthread API call is working properly. Okay, so let's go take a look at our start routine here, this find min function. So this is the function that each of the threads is going to run. Now remember that when we looked at the declaration for pthread create, it had a very specific data type for the start function. In particular, it was a pointer to a function that received as a single argument a void star and returned a void star as its return value. Now that seems like an awfully specific declaration, but because the parameters, or the single parameter and the return value are both void stars, we can basically pass a pointer to anything that we want and still access it from inside of our start routine. So it is really quite generic, and we need to, in order to keep the compiler happy, we need to define things that conform to that type for that function. So I've got a single parameter here that's I've declared to be void star. Keep the compiler happy. I've called it Threadargs. You can call it anything you want. That's just kind of a convention that makes it evident what's going on here. Now the issue here, though, is that we know, because of the way that we called this, or the way that we configured the pthread create, that what's going to be passed into here is actually one of these things, one of these Threadargs underbar T structures. But the declaration requires that we pass it as a void star, that we declare this as a void star, or we're going to get compiler warnings. In order to make it easy for us to access the contents of the thing pointed to by Threadargs as if it was a Threadargs T, which it is, because that's the way we set it up, the first thing I usually do inside of my start routines is take that parameter that I pass in and cast it to be the appropriate type of pointer, right? As far as the find min function is concerned, this guy is of a pointer to void, or just super generic pointer. That conforms to the definition of pthread create. But inside of here, I know, because I coded it, right, that this is really a Threadargs T pointer. I passed in the address of a particular Threadargs T that I set up down below in the main function. So I'm gonna cast this parameter as a Threadargs T, and I'm going to store a copy of the pointer in this args variable. Okay, so from that point forward, I can now refer to the things that I passed in here using this structure, as I hoped to be able to do. But this line here is just kind of there to convince the compiler, hey, this is okay. We're taking this pointer that we get passed in, and we're casting it to be a Threadargs T pointer, which we know is correct, right, because we set it up that way, and it keeps the compiler happy as well. So from here on in, we're just going to refer to these Threadargs through this args variable. And notice that that's defined to be a pointer to a Threadargs T, and that this is a pointer to a structure, so we're going to use the arrow operator inside of this thing to access the individual members. Now, just to kind of keep the code a little bit cleaner, in case you're still kind of wrapping your head around this structure pointer thing, I've elected to just create some local variables here called list pointer. That's a pointer to an int, right? That's going to be the pointer to the current integer that we're looking at. List size and local min. Okay, so I've set these things up and just initialize them right away, so we don't have to monkey around with a lot of arrows. So args arrow list pointer goes into this Threadargs T pointer structure and grabs the pointer to the first integer from big list that we're responsible for sorting. And similarly for the list size, right? I'm just kind of grabbing those things out of there to keep the code of the find min a little bit cleaner. It would be entirely fine to replace all the examples of list underbar pointer and list underbar size with args list pointer and args list size. And if it was me writing this code, or when you get more experience with this, that may be what you prefer to do. But again, I want to try to disentangle passing in the details for each thread from the actual thread code itself in this case. So you can do this if you want, you don't have to. Okay, next step is to find the local minimum, right? So we're going to iterate for I goes from 0 to the list size and take a look at list pointer of I. So we're using this list size that the main thread told us was the number of integers we wanted to search. And we're also using a pointer to an integer that the main thread told us was the first one to search at. And we're just treating that as an ordinary array, which it is, right? It's just a pointer to an integer, and pointers to things are the same as arrays of things in C. So for each of the values in that list, we're comparing it with our local min. And if we find a value that's smaller than our current idea of the local min, we're going to update local min, right? So super simple way of checking for the smallest value. You notice here that I actually internally here reinitialized local min to int max, which makes some sense because we're looking for the smallest value. So when we get here, at that point we know what it is, or we know the value of the smallest integer in our section of the original big list. Now what we want to do is check to see, is the value we have smaller than the previously found smallest value from a different thread. So now we're going to be maybe updating global min. Because we maybe are updating global min, and because all of the threads have access to global min, we gotta do something to prevent stepping on each other's toes. So we're going to now define a critical section. Again, a critical section is just something that's protected by a mutual exclusion primitive. So to enter the critical section, we have to be able to acquire the lock. So I've got mutex lock of that global min lock, and that was the thing that we defined up here. So either I'm going to be granted that lock if no other thread is holding it, and I'm going to be able to go to the next instruction, or I'm going to be blocked waiting for that lock to be available. And when somebody else releases the lock, I may be the next in series to get it, and then I'll be able to go forward. So when I get the lock, I'm going to check to see, is my local value stored here smaller than the global minimum that I have so far stored in static data, right? If local min is less than global min, well then set global min to local min. That's the only thing I have to do in terms of a critical section. So the next operation is going to be to unlock the mutual exclusion primitive to exit the critical section and let another thread have its chance to update the global minimum. Then here's the printf statement that prints that output that we looked at before. If I switch back to the shell, you can see P00, so many integers at some address, and the local minimum that I'd found. And that's exactly what we're showing here. And here's an example of using that thread ID. It's not really that critical in a relatively small program like this, but as your code gets larger, as the number of processors grows larger, it's really helpful to be able to sort of trace through what did each process do at different steps of the algorithm. So I'm printing out that thread ID, and I just use it as a little prefix. Then I'm printing out the list size, and it's reassuring to note that I get 16K as the value for the size, because that means I'm doing the right calculations when I'm starting up the thread. And then I'm printing out the location of the beginning of the array that I'm sorting and the local minimum that I found there. And that's what we see here in the output. So 16K integers at, and there's the pointer. Notice I'm using the %p formatting string inside the printf function, which prints out a pointer. And then I'm printing just a decimal value for the local minimum. So this thread found that as the local minimum, and so forth for the others. Okay. So that's just for kind of debugging output. And then finally, I'm going to set this local min value to be the local min. Remember, I have this thing, or these args, these Pthreadargs. I'm updating that last member with the local minimum that I found here. Now, this is really not strictly necessary in this case. If I didn't do this line at all, the algorithm would still work, right? Because what each thread is doing is it's updating that global minimum, And when all the threads are done, that global minimum will have the value. But I also wanted to illustrate here that in addition to updating a globally accessible variable like that global min, I can also use the threads to return additional information back from the thread, right? If I wanted to send back some performance data or other intermediate results or whatever, I can send that value back to the main function and make it accessible to the main function as part of the process of joining up with this thread. I also am going to introduce a new API call here. Pthread exit will exit the thread, and it's going to send back to the join the value here in its argument. Before the previous example, we didn't use pthread exit. We just sort of fell off the end of the thread, the start routine. That's a totally fine way to exit a thread as well. So if instead of doing this pthread exit, I could have here just said return args, and it would behave exactly the same way, right? So whatever suits your fancy in terms of returning a value back from the thread, you can just return something directly, or you can call pthread exit. The logic here, I think, is that in a normal process, when you're just running in a single thread, there's times when you want to kind of exit the process early, and you can call the standard exit, the exit function from the standard library. This is kind of the moral equivalent of that for exiting a thread without exiting the whole process. So you can do whichever way you want it to. I just wanted to illustrate the use of this. So what this does, whether we return the value or whether we call pthread exit with this value, is it makes that value available to the main function when we do pthread join. And again, I'm not doing this because I don't know the answer yet. I'm just doing this to sort of illustrate how to pass values into the function, right, using this parameter, and also how to pass things back from the thread function by using pthread exit. In this case, I'm actually passing back the same structure that I passed in. The only difference is going to be that I've updated the value of this local min argument inside of that structure. So again, it's not something that has to be done, but I just wanted to sort of illustrate in a concise way different ways that you can return values from these guys. I should also note that the mutex that I'm using here inside the thread function, which we declared up here, right, the global min lock, we also have to initialize that guy. So we can see down here in our setup code in main that I did in fact call pthread mutex init, passing in the address of that mutex and then using the default configuration attributes for that mutual exclusion primitive. So that's where it got set up. Then I spun up the different threads, and now that I've got the threads working, the only thing left for the main thread in this case to do is just wait for the threads to complete. So I'm going to enter another for loop, and I'm going to iterate over the threads, and I'm going to call pthread join. So the first call, or the first time through this loop, I'm going to call pthread join on threads of 0, which would be the 0th thread, and then loop through all of the threads. So regardless of which order the threads actually complete in, I'm only going to join them in the order that I've got here, going from 0 to 3. And you can see that here as well. The P00, P02, P03, P01, those are the thread IDs that are showing up in the order that those threads executed that instruction. So you can see thread 0 was on its way out before thread 2, before thread 3, before thread 1. However, this other line, thread 0 returned, that's coming out from right here. Those come up in sequence, right? 0, 1, 2, 3. Because whichever order, regardless of the order the threads terminated, this is going to call those in order according to the for loop itself. So you could run this 100 times and you might see different sequencing going on in the P00, 01, 02, 03, but thread 0 will always occur before thread 1, before thread 2, before thread 3. Okay, when we join the thread, what we can do here, and we didn't use this capability in the previous example, what we can do is pass as the second argument a pointer to some memory that we want to have filled in with the value that came back from the thread. So back up in the thread min function, right, this is where we set the value to be returned by the thread as this args structure. Well, that's what we're going to get back from the thread. So inside of inside this loop, I've declared another instance of this Threadargs t, right? That's our structure, not a Pthread specific thing, to store a pointer to that return information. So as the second parameter to Pthread join, I'm just passing up the address of that structure. Remember from the discussion the previous discussion, that thing is a void star star. It's a pointer to a void. So it's a pointer to a generic pointer. And again, that gives it the maximum flexibility to point to whatever we want it to point to. In this case, we want it to point to a Threadargs t so that we can go fish out the local value that was found for that particular subset of the array. So I'm passing in an address of a pointer, and in order to keep the compiler happy, I've got to say, pretend that that's actually a void pointer because that's what it's looking for. And then I'm printing that value out. So thread %d, well, there's thread I, again, that's kind of my artificial thread ID, has returned as its minimum the value from that thread return pointer, and because that's a pointer to that structure, I'm using the arrow to fish out the local min. So that statement is actually giving me back the value that I stored here, right? I updated that args structure to have that local minimum, and then down here I can fish that out from the main thread. So that, again, just kind of here illustrates how to pass things into the thread function and out of the thread function, and just allows us to get a little bit of a sanity check here when we look at our output. The thread itself thought it was returning 123.783, and the main function actually received 123.783, right? So it's just kind of a little sanity check to make us feel happier that everything's working. And finally, I print out the global minimum. And this again is that same global variable or file global variable here that's located in static data that all of the threads, including the main thread, have access to. So the main thread isn't updating that, it's just reading it out after it's waited for all of the child threads to complete, right? At the point we get to here, we will have joined all of the threads, and they will therefore have had time to update their idea of the global minimum, which is of course protected by that mutex, so we get a reliable value. So we print out the global min. And then also here I'm printing out the runtime. We have been saying that, you know, this is an empirical kind of part of computer science. Let's develop an algorithm and then kind of measure its performance. And the kind of fundamental measurement that we want to take is the parallel, or the time to run each of these threads, or each of these programs rather. So the runtime is an important thing to be able to measure, and I just wanted to introduce that really quickly here. So I've got a function that's defined up here called now. Super simple, fairly accurate actually. So it returns a double that is kind of the current time as of right now. So it uses a standard Unix structure called a time spec, which gives us the time in seconds and nanoseconds if the real-time clock supports that on the particular computer. So I just define a structure time spec here called current time, and then clock get time is a standard library thing. It's actually in this time.h library. That's a standard function that you can use that is going to grab the real-time clock. There's other clocks like per process things and whatnot, but that just tells us the current time of day basically, and it takes a pointer to this current time structure. So it fills in the number of seconds and milliseconds into that time structure, and then what I do for convenience is just convert that into a double precision floating point. So I take the current times TV sec, that's the number of seconds, and then add to that the current times TV nanoseconds, which is a number from 0 to 1 billion minus 1, and then I divide that by 1,000,000,000. That's what this other constant up here is about. So that this gives me a nice decimal representation of the current time. It's going to be the number of seconds since the beginning of the Unix epoch dot the number of nanoseconds. And that's just returned as a double. So we can use that to get our runtime. You'll notice that up here, I ran that function just before I started off all the threads, and I stored it in this double value called start time. And then when I got done, I have this print function that takes and it calls that now function again. So it gets the current time as of this statement right here and subtracts off the start time. So the total runtime comes out in this printf statement. If we go back to the output, you can see here the runtime was 0.000291109 seconds. So this took about 291 microseconds to run. Now that's going to become really important. Obviously, in this case, it's sort of silly to go through all this trouble to just find the smallest value in a relatively small array of 64,000 things. But when we start working on bigger problems, the times are going to get bigger, in some cases way bigger. But that's just a really simple way to measure the time. Notice also that, just one last note here, I'm measuring the time for this entire calculation, including the amount of time it takes to start up the threads, to run the threads, which they start running as soon as you do pthread create, and the time to wait for the threads to all terminate. There's overhead associated with those things, but that's something that we want to include in our measurement of the runtime, because it's taken into consideration when we're trying to calculate things like speed up and efficiency. We want to measure all of the sources of overhead that are due to having parallelized this particular problem so that we can compare it fairly against the runtime for a single process or a single thread in this case. So that's why I'm bringing in the values, or why I'm doing the calculation as I am for the runtime.